Hello class, this is lecture 8 and it's about we are going to build a VI to study the frequency response of an RC circuit. So as you can see here on my screen, so we are going to have like a resistor in series with a capacitor, and you're going to connect the function generator here. And you're going to connect the oscilloscope terminals, the positive to one end of the capacitor and the negative here. So in this experiment, we are going to provide a range of frequencies from 10K to 100K kilohertz and measure the peak to peak voltage of the sine wave at the capacitor. And then we are going to plot the frequency response. So let's get started with it. So we will first put an XY graph on our front panel and label this as frequency response. And this will be not time but frequency. Okay, and now we'll write our code. So I'm going to drop a for loop which has 10 iterations. Okay, and then I'm going to control the frequency using this iteration terminal. Like we did in the earlier example with diode. Create constant, and I will give an increment of 10K. So this will be 10,000, 2, 3, yeah. And then I'm going to have a sequence structure. So in the first frame, we are going to set the frequency of our sine wave of our in our function generator. So, and in the second frame, we are going to use the second frame to to record the voltage values at our capacitor. So add frame after. Okay. I like to use the stack sequence. Okay. Add frame after. Okay. So now we will initialize the function generator. For that, we have to go to the Chillant function generator, initialize. So now let's connect this. Create constant has to be analog discover. So this is our frequency terminal. So we would like to connect the frequency here. We are going to control the frequency. Duty cycle, create a constant of 50. Waveform function, create constant. This time we want to just have a sine wave. And amplitude, create constant 2 volts. And then what do we have next? DC offset, create constant of 0. Okay, and now we're just going to close this. Let's move this here. Change it to the last value. This. So we're going to add shift register here. Delete this. Okay, and then we're going to add the dialog. Simple error handler VI. Okay. Then next, in the second, okay, yeah, I did not finish this one. Okay, so in the second data frame, we are going to first we're going to initialize the oscilloscope. Connect the device name. And then we have the configuration. So I have dropped in all these sub VIs here for initialization and configuration, and I will connect them now. So I have connected them, and also I have given the channel name and set up these constants. And now, so now I'm going to use the index waveform array to extract the data from channel 1. If you're using channel 2, then put here as 1. And then we want to read the peak to peak amplitude value here. So just gonna use signal processing waveform measure. Amplitude and frequency, just to make sure we are receiving the same frequency here. Okay, I think I have chosen the wrong one. This is waveform measure, extract tone. If it is multiple, then extract tone. So we are just dealing with one channel, one array. So connect it here, and we can create an indicator for this. This is similar to the lab 6. Create, oh no. Create indicator. So detected amplitude, and this is the detected frequency. So by seeing the detected frequency, we can make sure we are receiving the correct frequency, and the detected amplitude will give us the peak to peak voltage. Across the capacitor. We'll give the peak to peak voltage across the capacitor. So now we intend to plot the on the x-axis the frequency. So let us add a sequence local so we can pass it on to the other frame, and then just connect it here. And then we have the x values here, and we have the y values here. So what I have done is I have added, I have used the bundle function, the x values and y values. So I've used the bundle function and then plotted using frequency response. So this is something we did earlier even. So we have plotted once with the bundle function, and another way of doing this is by using a dynamic data type. Like this is like you're converting the array to a dynamic data type. So the way you can do is go to signal processing. Oh no, sorry, express VI, and then you go to signal manipulation, and then choose from okay, 2DDT stands for dynamic data type. So it will convert, let's take it here. And then here you need to so you need to select 1D array of scalars and single channel because that's what we have right now. And you can learn more about it using the help option. So as you can see, it converts a numeric Boolean waveform and array data types to dynamic data types. So, and then you can use the build XY graph. This is also an express VI. So you give like X and Y values and then plot it. So these two are the same ones, like you can, this is optional whether you do it or not. I just wanted to show you an alternate method of doing this. It's not mandatory though. And so yeah, and you can just move this inside if you want, and just move this inside, and then we can just run the code and see what is the kind of output we are getting. So this is like from the other graph that I just placed right now. So let's run this. The output will be the same anyways. Yeah, so this is the response, a frequency response of a low pass filter. So this is how you get. Sometimes you might, because of the loose connections, you might not get a proper graph. So just make sure that the circuit connections are proper, because that was something that one of the problems that I was facing. And then I realized that some of the connections are loose. I kind of have this artifact. I don't know why. In previously, I got like a smooth curve. I have just realized that the the sample rate plays a very important role when you the reason for getting like artifacts or distortions in your graph is because of your sample rate. So now I have set my sample rate to about 50 megahertz, and also have increased the iteration number by 1, because I want to go from 10K to 100K. So for that, since our I starts from 0, therefore we have to do like 11 iterations. So this is the kind of graph I got, but I can still run it for you again. Data operations, clear graph. So yeah, after changing you can try it yourself. When you set a sampling rate, a lower sampling rate, you get like a distorted curve. But when you set it like to about 50 megahertz, you will get a proper graph. See, now I got a proper graph here. So the reason is, like, when I set it to, I think previously I have set it to 100,000 samples per second, the sampling rate. And I was trying to detect something in about till 90K, and it wasn't like able to, the oscilloscope wasn't able to read them because of the Nyquist theorem. So therefore we weren't getting proper values. But now we can see that we have almost like reached up to 100K, and we have like a proper graph here. And yeah, so just wanted to remind you of that. So we are going to study the frequency response of an RC circuit. Therefore, I have first put an XY graph and then labeled it as frequency and amplitude. And then coming to the block diagram. So the first thing that we want to do is we want to have like, we want to send like different frequencies to our function generator from about 10K to 100, from 10K to 100K. So we create a for loop and we are going to run 11 iterations, and then we are going to give a step size of 10,000, and we have put a sequence structure here. So in the first, we want to initialize our function generator and then set it to a certain frequency. And then we want to read the voltage across our capacitor, the peak to peak voltage. So in the first data frame, so outside the loop, we have initialized it. We have given the device name and the channel number. I'm using the channel 1. And then we use the run sub vi configure, and then we have the close one just outside the loop. So I have set this to constant, like constant duty cycle, constant like waveform. I'm just going to use a sine waveform, and the offset is set to 0, and the amplitude is also set to a constant value 2. And we are going to increase the frequency with the step size of 10K. And then in the data frame 2, once the input voltage is set, then we are going to use the oscilloscope. So we have like configured it, used the time, we have done the timing settings, and then we are going to extract the data from the channel 1 and then find out the peak amplitude and the frequency. And then we are going to simply use a cluster function and then plot it on the XY graph. Just make sure that it is set to indexing, because we want to create an array of these values and then send it to the cluster. And then send it to the bundle. And yes, so we have our program ready. And then when we run this, oops, sometimes the device need to be reset, otherwise it will create problems like this. So you can just plug out your device, wait for 10 seconds, because sometimes the port is really busy. So you can wait for 10 seconds and then connect it. And then run it. So we get the graph like this. Yeah, and we see that the detected frequency is 99K, and the amplitude, or the voltage value across the capacitor, is 4 millivolts. So yeah, we have successfully seen the frequency response of a low pass circuit. Thanks for listening. So because I'm getting issues like when I try to run it more than once, like you saw previously, I was having problems. So I just tried using putting a reset button and connecting it to the reset terminal of the function generator and also my oscilloscope. So they have a terminal called reset. So this makes it very easy, like you can run it multiple times. You don't have to plug in and out the device, and you can do this to all your for all your LabVIEW programs with AD2. So like when I turn the reset on and I try to run it multiple times, I see that it's giving me a proper graph. I don't get any distorted graphs anymore, and I don't have to plug in and out my device. See. Okay, thank you.